If you're wondering, this is how the most revolutionary course in biology of all time begins. Come today to learn about covalent and ionic and hydrogen bonds. What about electron orbitals and the octet rule? And what does it all have to do with a madman named Gilbert Lewis? It's all contained within. Hello, I'm Hank. I assume you're here because you're interested in biology, and if you are, that makes sense, because like any good 50 Cent song, biology is just about sex and not dying. Everyone watching this should be interested in sex and not dying, being that you are, I assume, a human being. I'm going to be teaching this biology course differently than most courses you've ever taken in your life. For example, I'm not going to spend the first class talking about how I'm going to spend the rest of the class. I'm just going to start teaching you, like right about now. I may say one more thing before I start teaching. Yes, I am going to. It's that if I'm going too fast for you, great thing about YouTube is that you can just rewind, watch stuff over and over again if it's confusing, and hopefully it will become less confusing, and you're even allowed to fast forward through the bits that you already know. Another tip, you can actually even use the number keys on your keyboard to move around in the video, and I promise, you can do this to me as much as you want, and I'm totally not going to mind. A great professor of mine once told me that in order to really understand any topic, you have to understand a little bit of the level of complexity just below that topic. The level of complexity just below biology is chemistry. Unless you're a biochemist, in which case you would argue that it's biochemistry. Either way, we're going to have to know a little bit of chemistry in order to get through biology. And so that, my friends, is where we're going to start. I am a collection of organic molecules called Hank Green. Organic compounds are a class of compounds that contain carbon. And carbon is this sexy little minx in the periodic table that's, you know, disinterested in monogamy. Jezebel. Bit of a tramp. Hussy. When I say carbon is small, I mean that it's actually, you know, as an atom, it's a relatively small atom. It has 6 protons and 6 neutrons for a total atomic weight of 12. Because of that, carbon doesn't take up a lot of space. And so carbon can form itself into weird rings and sheets and spirals and double and even triple bonds. It can do all sorts of things that could never be accomplished by more bulky atoms. It's basically, you know, your atomic equivalent of an Olympic gymnast. It can only do all of those wonderful, beautiful, elegant things because it's kind of tiny. I also said that carbon is kind, and that's an interesting sort of thing to say about an atom. It's not like some other elements that are just desperately trying to do anything they can to fill up their electron orbitals. No, carbon knows what it's like to be alone, and so it's not all, please, I'll do anything for your electrons, needy like fluorine or chlorine or sodium is. Elements like chlorine, if you breathe them in, they like literally tear up your insides, and sodium is insane. If you like put it in water, it explodes. Carbon though, meh. It wants more electrons, but it's not gonna like kill to get them. It makes and breaks bonds like a 13-year-old mall rat, and it doesn't even hold a grudge. Carbon is also, as I mentioned before, a bit of a tramp because it needs 4 extra electrons, and so it'll bond with pretty much whoever happens to be nearby. And also, because it needs 4 electrons, it'll bond with 2 or 3 or even 4 of those things at the same time. And carbon is, you know, willing and interested to bond with lots of different molecules, like hydrogen, oxygen, phosphorus, nitrogen, or to other molecules of carbon. It can do this in infinite configurations, allowing it to be the core atom of complicated structures that make living things like ourselves. Because carbon is this perfect mix of small, kind, and a little bit trampy, life is entirely based on this element. Carbon is the foundation of biology. It's so fundamental that scientists have a pretty difficult time even conceiving of life that isn't based on carbon. Life is only possible on Earth because carbon is always floating around in our atmosphere in the form of carbon dioxide. So it's important to note, when I talk about carbon bonding with other elements, I'm not actually talking about sex. It's just a useful analogy. Carbon, on its own, is an atom with 6 protons, 6 neutrons, and 6 electrons. Atoms have electron shells, and they need to have these shells filled in order to be happy, fulfilled atoms. So carbon has 6 total electrons, 2 for the first shell, so it's totally happy, and 4 of the 8 it needs to fill the second shell. Carbon forms a type of bond that we call covalent. This is when atoms actually are sharing electrons with each other. So in the case of methane, which is pretty much the simplest carbon compound ever, carbon is sharing sharing its 4 electrons in its outer electron shell with 4 atoms of hydrogen. Hydrogen atoms only have 1 electron, so they want their first s orbital filled. Carbon shares its 4 electrons with those 4 hydrogens, and those 4 hydrogens each share 1 electron with carbon. So everybody's happy. In chemistry and biology, this is often represented by what we call Lewis dot structures. Good Lord, I'm in a chair. I'm in a chair and there's a book. Apparently I have something to tell you that's in this book, which is a book called Lewis, Acids and Bases, by Hank Green. Gilbert Lewis, the guy who thought up Lewis dot structures, was also the guy behind Lewis Acids and Bases, and he was nominated for the Nobel Prize 35 times. This is more nominations than anyone else ever in history, and the number of times he won is roughly the same number of times that everyone else in the world has won, which is 0. Lewis disliked this a great deal. It's kind of like a baseball player having more hits than any other player in history and no home runs. He may have been the most influential chemist of all time. He coined the term photon, he revolutionized how we think about acids and bases, and he produced the first molecule of heavy water. And he was the first person to conceptualize the covalent bond that we're talking about right now. Gilbert Lewis died alone in his laboratory while working on cyanide compounds after having had lunch with a younger, more charismatic colleague who had won the Nobel Prize and who had worked on the Manhattan Project. Many suspect that he killed himself with the cyanide compounds that he was working on, but the medical examiner said heart attack, without really looking into it. I told you all of that because the little Lewis dot structure that we use to represent how atoms bond to each other is something that was created by a troubled, mad genius. It's not some abstract scientific thing that's always existed. It's a tool that was thought up by a guy, and it was so useful that we've been using it ever since. In biology, most compounds can be displayed in Lewis dot structure form, and here's how that works. These structures basically show how atoms bond together to make up molecules. And one of the rules of thumb when making these diagrams is that the elements that we're working with here react with one another in such a way that each atom ends up with 8 electrons in its outermost shell. That is called the octet rule, because atoms want to complete their octets of electrons to be happy and satisfied. Oxygen has 6 electrons in its octet and needs 2, which is why we get H2O. It can also bond with carbon, which needs 4, so you get 2 double bonds to 2 different oxygen atoms and you end up with CO2. That pesky global warming gas, and also the stuff that makes all life on Earth possible. Nitrogen has 5 electrons in its outer shell. Here's how we count them. There are 4 placeholders. Each of them wants 2 atoms. And like people getting on a bus, they prefer to start out not sitting next to each other. I'm not kidding about this. They really don't double up until they have to. So for maximum happiness, nitrogen bonds with 3 hydrogens forming ammonia, or with 2 hydrogens sticking off another group of atoms, which we call an amino group. And if that amino group is bonded to a carbon that is bonded to a carboxylic acid group, then you have an amino acid. You've heard of those, right? Sometimes electrons are shared equally within a covalent bond, like with O2. That's called a nonpolar covalent bond. But often, one of the participants is more greedy. In water, for example, the oxygen molecule sucks the electrons in and they spend more time with the oxygen than with the hydrogens. This creates a slight positive charge around the hydrogens and a slight negative charge around the oxygen. When something has a charge, we say that it's polar. It has a positive and negative pole, and so it's a polar covalent bond. Now let's talk for a moment about a completely different type of bond, which is an ionic bond. And that's when, instead of sharing electrons, atoms just completely, wholeheartedly donate or accept an electron from another atom and then live happily as a charged atom. And there actually is no such thing as a charged atom. If an atom has a charge, it's an ion. Atoms, in general, prefer to be neutral, but compared with having a full octet, it's not that big of a deal. Just like we often choose between being emotionally balanced and sexually satisfied, atoms will sometimes make sacrifices for that octet. The most common ionic compound in our daily lives is salt. Sodium chloride, NaCl. This stuff, despite its deliciousness, as I mentioned previously, is made up of 2 really nasty chemicals, sodium and chlorine. Chlorine is what we call a halogen, which is an element that only needs 1 electron to fulfill its octet, and sodium is an alkali metal, which means that it only has 1 electron in its octet. So chlorine and sodium are so close to being satisfied that they will happily destroy anything in their path in order to fulfill their octet. And thus, there's actually no better outcome than just to get chlorine and sodium together and have them loving on each other, they immediately transfer their electrons so that sodium doesn't have its one extra and chlorine fills its octet. They become Na+ and Cl- and are so charged that they stick together, and we call that stickiness an ionic bond. And just like if you have two really crazy friends, it might be good to get them together so that they'll stop bothering you. Same thing works with sodium and chlorine. You get those two together and they'll bother no one. And suddenly they don't want to destroy, they just want to be delicious. Chemical changes like this are a big frickin' deal. Remember, chlorine and sodium just a second ago were definitely killing you, and now they're tasty. Now we're coming to the last bond that we're going to discuss in our intro to chemistry here, and that's the hydrogen bond. Imagine that you remember water. I hope that you didn't forget water. Since water is stuck together in a polar covalent bond, the hydrogen bit is positively charged and the oxygen bit is negatively charged. So when water molecules are moving around, we generally think of them as a perfect fluid, but they actually stick together a little bit. Hydrogen side to oxygen side. You can actually see this with your eyes. If you fill up a glass of water too full, it will bubble at the top. The water will stick together at the top. That's the polar covalent bonds sticking the water molecules to each other so that they don't flow right over the top of the glass. These relatively weak hydrogen bonds happen in all sorts of chemical compounds. They don't just happen in water, and they actually play an extremely important role in proteins, which are the chemicals that pretty much make up our entire bodies. A final thing to note here is that bonds, even covalent bonds, ionic bonds, even with their own class, are often much different strengths, and we tend to just write them with a little line. But that line can represent a very, very strong covalent bond or a relatively weak covalent bond. Sometimes ionic bonds are stronger than covalent bonds, though that's generally not the case, and the strength of covalent bonds varies wildly. How these bonds are made and broken is intensely important to life and to our lives. Making and breaking bonds is, in fact, the key to life itself, and also the key to death. For example, if you were to ingest some sodium metal. Keep this in mind as we move forward through biology. Even the sexiest person you have ever met in your life is just a collection of organic compounds rambling around in a sack of water. Review time! Now we have the table of contents, which I know is supposed to come at the beginning of things, but we are revolutionary here. We're doing it different. So you could click on any of the things here and you can go back and review what you learned or didn't learn. And if you have questions, please ask them in the comments, and we'll be down there answering them for you. So thank you for joining us. It was a pleasure. It was a pleasure working with you today.